Hi students, how are you? Hope you all had a great, wonderful, enjoyable weekend. I hope slowly but surely you are getting settled and getting used to the electromagnetic theory. As I mentioned in the last video, don't get scared about the mathematics. So, mathematics should follow you. You should not go and follow mathematics. So, once you are confident about the concepts, mathematics will automatically follow you. Now, the agenda for this particular class, this particular video, is going to be very simple and straightforward. Here, we are going to attempt to derive a relationship between electric field, which is a vector quantity, and thankfully, electric potential, which is a scalar quantity. Why I said thankfully? Because we need not bother about the directions. We need not really worry whether the sign is going to be positive or negative. So, because potential can be positive, potential can be negative, you can have zero potential. So thank God we are not going to anymore deal with the vector concepts when it comes to the electric potential. However, electric field is a vector quantity, so we have to be very careful on that. Now, how are we going to derive a relationship between electric field and electric potential? Let's get on with an example. So what are we going to do first? Let's say that you have a hollow sphere, and this particular sphere is having a radius of r, and let's imagine that this particular sphere is uniformly charged plus q on its surface. It contains a charge of plus q on its surface. Now let's pick a point outside the sphere and let's draw a straight line to this particular point. So let's call that point as P. Now we would like to calculate the electric potential at this point Vp. That's going to be the agenda for this class. So how are we going to calculate? Just as we did in the last class. So let's assume that the electric potential at P is always going to be the work done in moving a test charge through a distance dr. So let's say that we are going to sum up in terms of an integral. So this is going to be the electric potential is going to be the integral of taking a test charge in your pocket and walking from r to infinity, and the force involved is going to be electric force. This is going to be away from the positive test charge, and the electric force is going to travel a displacement, and that displacement is dr, and then the test charge has to be included here. So this is your work done, and this is the test charge, the work done over a given unit charge. That's going to be the electric potential. Now this particular term, what is this? You may be knowing it. Just recollect, this particular term is nothing but your electric field. So electric field is always, please don't forget this formula, is force separated by charge. So what we are going to do here is, so we are going to put integral r to infinity, and we are going to write this is nothing but the dot product of electric field and the displacement. Now the direction of the electric force is, let's do with another color. It's always boring to have one color. So let's say that the direction of the electric force is going to be along this direction, away from the positive test charge. Now the direction of the unit vector is going to be somewhere here, r cap, and since both dr and the electric force is along the same direction, this dot product disappears. So as a result of which, cos theta is going to be 1 because theta is going to be 0. So effectively cos theta is 1. So we have got rid of this particular big headache of vector quantities. So all we are going to get is E dr. So this is going to be nothing but integral r infinity. So this is E is kq over r square, so that can be written as dr by r square. So if you do the integral, you're going to get kq by r, which is nothing but your electric potential. So electric potential in this way can be related to the electric field. So electric potential is nothing but the integral of the electric field. So you can say that if the electric potential difference is uniform and if the electric field is uniform, then we can say that it is nothing but the product of E and R lying in the same direction. So this is the formula that relates the electric potential difference and the electric field. Now let's look at another situation. So let's choose 2 points. So let's take a point A and let's take another point B. These 2 points are separated by a distance r. The potential at this particular point is going to be VA. The potential at this particular point is going to be VB. So what is the potential at VA? It's very simple. It is the work done in moving a test charge from A to infinity. So that is A to infinity, and we have already seen that this work done in moving a test charge can be written in terms of the electric field, the dot product of electric field and the displacement. In a similar way, you can write the potential at B is the work done in moving a test charge from B to infinity. So that's going to be like this. So to summarize, we can say that the potential difference AB is going to be the work done in moving a test charge from A to B, which is nothing but E dot dr. Well, the textbooks, for some strange reason, write this as VBA and put a minus sign, and they do write this as minus of integral A to B electric field dot the displacement dr. So you can say that electric potential difference delta V for any electric field, uniform or non-uniform, is always the negative integral of the electric field. So electric potential is nothing but the integral of the electric field. So I hope the relationship is very clear. Now let's take another interesting situation. Let's say that we'll take a single point A and let's take an arbitrary distance and let's mark this point as B. Let the distance, as usual, the separation P, let the distance of separation be R. Now what would be the electric field at P? Very simple, it is elementary, kq over r square. We have done this a million times. What will be the potential at P? Once again, it's very easy, it's going to be kq by r. So this is second equation. Now the electric potential, I can say that, is the integral of the electric field. Similarly, can the electric field be the derivative of the potential? That's what we have to see now. So what are we going to do? So we are just going to write V is equal to kq by r. Then we are going to differentiate this dv dr. So that will become minus kq by r square. The differential of 1 by r is minus kq by r square. Now mind you, electric potential is always a scalar quantity, so we need to make this as vector. So if you multiply both LHS and RHS by R cap, which is perfectly legal to do so, you will be having dV dr R cap will be minus kq by R square R cap. So this entire term we know is nothing but our electric field. So we can say that electric field is negative of the differential of the potential. So this is another relationship which is used oftentimes. So to summarize, we can write the relationship between, sorry, oops. So we can use different color codes. Let's use blue. Blue looks very pleasing. So we can say that the electric potential is, or you can say the electric potential difference between any 2 points is the integral of the electric field. Similarly, you can say that the electric field is differential of the electric potential. Of course, you have to put a minus sign before that. So this is how the relationship between electric field and electric potential stands out. In the next class, we will definitely look into some problems. We will talk about equipotential surfaces, and once again let us take the Cartesian coordinate system, and let's see how this particular electric field in terms of Cartesian coordinate system will be minus grade B. This is what we are going to see in the next class in detail after looking into a problem. Have a nice day. Thank you very much. Until then.